What can we do with an image? The very question behind all computer vision research. Nowadays, as deep learning continues to revolutionize the landscape, the answer could only be more and more. For instance, state-of-the-art object detectors are now reliably detecting humans, vehicles, animals, etc. So what more can we do? Well, how about finding the interactions between them? So in the image on the first row, instead of simply localizing the people and the bikes, we can try to understand which pairs of humans and bikes are engaged in the interaction riding a bike. Well, as it turned out, this is hard for deep neural networks. One of the most powerful pieces of machinery, the convolutional neural networks, or CNNs, are exceptional at recognizing textures and shapes, but not so much at spatial reasoning. Is the person in an orange vest riding a bike? And amongst all these people, who's riding which bike? The truth is, CNNs can find these people and the bikes easily, but have a hard time figuring out the correspondence. As a contrast, we as a noble species are able to infer complicated interactions from not just the visual cues of the scene, but the interrelationship of what compose the scene, objects. Perhaps we ought to build a model that can understand the intricacy of such interrelationship and perform structured prediction. So we did. We decided to construct a bipartite graph to model such interrelationship, with human nodes on one side of the bipartition and object nodes on the other. To zoom in on a pair of nodes, let's look at figure 2b. Start from the middle. The two circles represent the pair of human and object nodes with appearance features. The edge features in between are learned representations of their spatial relationships, which is key to our spatial reasoning. Going to the left, message sent from a node is computed using the node features and edge features through the proposed multi-branch fusion. To the right, the adjacency, which is a weight on the message, is computed in a similar way. Weighted messages will then be used to update the node encoding. Upon finishing message passing, we use the same fusion module for adjacency but different logistic layer to compute class probabilities. Finally, what does multi-branch fusion do? Well, we first use linear layers to map the two inputs to the same dimension and then apply element-wise product. But there's a twist. Instead of performing this operation once, inputs are mapped to multiple subspaces with reduced dimensions, followed by identical operations. This design of homogeneous branches, inspired by ResNext and transformer models, allows each branch to specialize and attend to different details without introducing extra parameters. With that remark, I conclude this talk.